So in the last video, we did some pretty intense chain rule examples. You might think that would be a good way to end this section, and probably it would be, but it doesn't quite cover everything that I want to talk about. There's a few different things kind of left over, and I'm going to throw all those things into this video. So first, just another example. Suppose you have this function f of x. It's equal to the cubed root of the natural log of x squared minus 8 to the third power. Suppose you're asked to figure out f prime of 3. Well, to figure out f prime of 3, maybe a logical starting spot is to figure out f prime of x. F prime of x would just be the derivative of this function, the cubed root of the natural log of x squared minus 8 cubed. Instead of copying here exactly what you see written here, I'm going to switch from radical notation to exponent notation, kind of thinking ahead about what forms are conducive to my derivative rules. So I'll say that f prime of x is equal to the derivative of something raised up to the 1/3 power. That something is a huge mess. The natural log of x squared minus 8 raised up to the third power. I think I've got all my parentheses right here. Don't be too overwhelmed with the fact that this is going to end up being chain rules inside chain rules, kind of like we saw in this example from the previous video. For now, just focus on the outermost layer. If you can recognize that the outermost layer is this cubed root of x, which I can rewrite as stuff to the 1/3 power, then you can get started on this huge problem. My first step would be to use the power rule. I'm going to take this 1/3 and bring it down in front, and my new exponent will be 1 less than that 1/3. In other words, negative 2/3. Don't be intimidated by all this stuff. For now, I'm just leaving it alone. The natural log of x squared minus 8 to the third power. But as hopefully you know, we're not done at this point. We still have to multiply by the derivative of all that stuff. The derivative of the natural log of x squared minus 8 raised up to the third power. But really, don't worry about that mess right now. We have another chain rule going on here, and the outer layer of our chain rule is what's pictured in green. This first factor is completely done. It's just along for the ride. For this second factor, I want to take the derivative of the natural log of some stuff. Because the derivative of natural log of x is 1 over x, the derivative of the natural log of some stuff is 1 divided by all that stuff, x squared minus 8 to the third power in this case, times the derivative of that stuff. Again, x squared minus 8 to the third power. As the color coordination might imply, we have one more layer of the chain rule to deal with. This problem is actually a chain rule inside a chain rule inside a chain rule. It's a composition of 4 different functions, which is pretty wild. But the good news is, as long as you know how to apply the chain rule, you're not doing anything new in each of the different layers. Just always focus on the outermost layer. All the stuff in brown now is just along for the ride. I'm focusing on this red layer, the stuff raised up to the third power. To take that derivative, I use the power rule. I bring the 3 down in front. My new exponent is a 2. I leave the x squared minus 8 completely alone inside these parentheses, and then I multiply by the derivative of that x squared minus 8. I'm finally done with iterations of the chain rule. All the stuff in brown is along for the ride. All that's left to do is take this derivative in orange. The derivative in orange is the derivative of a sum. The sum of x squared and negative 8 in this case. The derivative of x squared is just 2x. The derivative of the negative 8 is a 0, so this derivative is 2x plus 0, in other words, 2x. If you've made it this far, I'd be thrilled. I'd love to see that as your final answer. However, I'm not going to leave my answer this way because a couple things jump out at me. First of all, I have x squared minus 8 to the third power down here in the denominator, and I got x squared minus 8 to the second power over here. I can think about this as up in the numerator. That'll allow me to cancel out this entire x squared minus 8 squared with 2 of the x squared minus 8s that make the x squared minus 8 cubed in the denominator here. That'll simplify things quite a bit. I can also cancel out this 1/3 and this 3, and what that'll leave me with is just a 2x up in the numerator for this 2x right here. Down in the denominator, I'll have the 1x squared minus 8 that netted out from this and this. And then I'll have this entire mess that's raised up to the negative 2/3 power. Because the exponent's negative, I can write it down on the bottom. An exponent of 2/3 means the cubed root of something squared. That something is the natural log of x squared minus 8 cubed. I think I've collected all the different factors here, put them together into this fraction. I think I would call this good. Although I want to be really clear, from here to here is hard algebra, but it's not hard calculus. The calculus, which itself was very, very challenging, happened from this line down to this line. You're like, all right, it's hard, but at least we're done. Well, not quite, because we just figured out f prime of x, right? We figured out a machine that tells us the slope of the tangent line to this function f of x at any value x. But that's not what was asked. What was asked was to find f prime of 3. The nice thing about f prime of 3 is it's relatively easy to figure out if you know f prime of x. All I got to do is copy exactly what I see here, changing all of the x's into 3's. So I would have 2 times 3 up in the numerator. I'd have 3 squared, or 9, minus 8 in these parentheses. So I'd have 1 in these parentheses. And then I would have the cubed root of something squared. That something is the natural log of 3 squared minus 8, which is 9 minus 8, which is 1, cubed. So it looks kind of ugly, but it simplifies really nicely. 2 times 3 is just 6. 1 times anything is just that anything, so I can drop this 1. 1 cubed is equal to 1, and the natural log of 1 is equal to 0. That 0 squared just gives me 0. The cubed root of that 0 is just 0, and that 0 times this 1 is just 0. What I'm saying is f prime of 3 is 6 divided by 0. And you're like, what? 6 divided by 0? Isn't that undefined? You must have messed something up. That can't possibly be what you intended the answer to be. In fact, it is. It's exactly what I wanted the answer to be. What does that mean? Why am I asking you to interpret your answer? Because generally, f prime of 3 tells you the slope of the tangent line to a curve at a given point. So f prime of 3 tells you the slope of the tangent line to this curve when x equals 3. But how can that be? How can a slope be undefined? Let me show you. Here's a graph of this function, the cubed root of the natural log of x squared minus 8 cubed. Kind of an interesting looking graph, right? What we're interested in is this point right here where x is equal to 3. Maybe I can zoom in a little bit. The first comment is when x equals 3, y equals 0. We can confirm that by plugging 3 into this equation. The same thing will kind of happen. We'll take the natural log of 1, which is just equal to 0, and that'll produce the 0 that determines this height. But that's not the 0 that's interesting. The 0 that's interesting was the denominator of this fraction that represents the slope of the tangent line. It almost makes it look like you couldn't draw a tangent line at this point. But that's not the case if you look at the graph. You could absolutely draw a tangent line right here. The problem is that tangent line would go straight up and down. That tangent line would be vertical. And maybe you remember that the slope of a vertical line is undefined, because what the slope tells you is how much the graph goes up each time you take one step to the right. And if you have a vertical line, that graph goes straight up and down. It doesn't go to the right. So I can't answer the question, how much does it go up when I go one step to the right? Because it never goes to the right. All this means in this case, to have an undefined derivative at this point, is that the tangent line to this curve is vertical. And you're like, yeah, fine, whatever, who cares? That's more interesting than you might think, because it brings about this paradoxical behavior. How can the tangent line be vertical? What that means is that at this instant, the graph is going straight up and down. But if the graph is going straight up and down, its x-coordinate is not changing, which means its x-coordinate is stuck at 3. But anytime the x-coordinate is 3, we know the tangent line is vertical. So we can never, loosely speaking, get off of that x equals 3. We can never get to another x value because the graph's supposed to be going up and down. But as you can see, that doesn't actually happen here for some very paradoxical reasons involving infinities and limits and all sorts of craziness. I don't want to get too far beyond the scope of the class. I just wanted to make the observation that it's entirely possible to have a vertical tangent line to a curve like you see in this specific function. And when that happens, evaluating the derivative at that point will produce an undefined output. Strange, but if you understand what's going on, not quite as strange. That's the first thing that was kind of left over that I wanted to throw into this video. I have 2 more things. None of them are really that related. The second one I think you're going to like. Not that I didn't think you'd like that one, but I think you'll like this one a little bit more. Suppose I have this function g of x. It's equal to the natural log of the square root of x squared e to the x. Maybe you can see we got all sorts of chain rule going on here. If we had to take the derivative of this, it'd be kind of a mess, right? Our outermost function would be the natural log. The next layer of function would be stuffed to the 1/2 power for this square root sign. And then the final layer would be a product. I guess we'd have a product rule inside 2 chain rules. It would be a mess, but we could figure out that derivative if we really wanted to. G prime of x is within our grasp, but G double prime of x might not be. I mean, imagine what that's going to look like. I'll do it for you if you want. I'll do it without showing any work at all. If I were taking the derivative of g of x, if I wanted to find g prime of x, I'd first take the derivative of the natural log layer, which would give me 1 over the rest of the stuff, square root of x squared e to the x. But then I'd have to multiply by the derivative of that stuff, the derivative of the square root of x squared e to the x. Well, I can think about that as x squared e to the x to the 1/2 power, so that when I take the derivative, I bring the 1/2 down in front, leave the rest of the stuff alone. My new exponent is 1 less, in other words, negative 1/2. What I have left inside these parentheses is x squared e to the x. But I'm still not done. I have to multiply that by the derivative of x squared e to the x. This is a product of two things. So to take the derivative, I need to use the product rule. The product rule tells me the derivative of x squared e to the x is the derivative of x squared, aka 2x, times the e to the x, plus the derivative of e to the x, which is just e to the x, times x squared. This huge mess right here is my first derivative, which is fine. I mean, I can simplify it a little bit and make it prettier. But if you didn't simplify this and you tried to find the second derivative, it would be a nightmare. I mean, we'd have a product of three things, so we'd have our super product rule in there. Several of those things that we're multiplying together would involve the chain rule. There's more product rules hidden inside there. It would take forever. You could fill up a whole page taking the derivative of this expression, especially if you're showing your steps like I encourage you to do. You're like, yeah, I know. You've made this point before. Simplify this before you take another derivative. No, that's not the point that I'm trying to make. The point that I'm trying to make is there's a way to make g prime of x much easier to find. In fact, you don't have to use the product rule or the chain rule to figure out the derivative of the natural log of the square root of x squared e to the x. And you're like, that can't possibly be the case. I see functions composed together and I see multiplication. How are you going to get around using those rules? The way I'm going to do it is by using some log rules. You may or may not remember log rules from a pre-calculus class. If you're like most students, you do not remember at all. But maybe if I write them for you, that'll kind of ring a bell. At one point in your mathematical background, you were supposed to have learned that anytime you're taking the log of a product, doesn't matter what the base is, the log of anything times anything, you can rewrite that as the sum of two different logs. In my pre-calculus class, I refer to this as the first log rule, although there's no real meaning to the numbering of them. The second log rule is really similar. It says that instead of a product that you're taking the log of, if it's a quotient you're taking the log of, well, you almost end up with the same thing, except instead of adding the two logs, you subtract the two logs. Kind of makes sense since multiplication is similar to division, addition similar to subtraction. Maybe you can talk yourself into why these would be true. The third log rule looks completely different, but it's every bit as useful. It says if you're taking the log of something raised up to an exponent, you can move that exponent down in front and multiply it by the log. This feels a lot like our power rule, but it's not. There's no calculus going on here. This is just algebra. It's only coincidence that it kind of works the same way our power rule does. These are the three log rules, and if you have these handy, you can do a lot of simplification to this function before you ever take the derivative. We've seen this many times in this class. If you can simplify before you do the calculus is often a lot easier. So how can we simplify this? Well, we want to take the derivative of the natural log of the square root of x squared e to the x. You can think about that as the natural log of x squared e to the x raised up to the 1/2 power, because taking the square root of something is the same as raising it to the 1/2 power. What I have written here fits my third log rule. Playing the role of this x right here is x squared e to the x, and playing the role of this t right here is this 1/2 power. So I can bring this 1/2 power out in front of the natural log. So instead of figuring out this derivative, I can figure out the derivative of 1/2 times the natural log of x squared e to the x. Already things are getting easier, right? Because exponents involve another layer of rules, but coefficients do not. Coefficients are really nice in calculus. We get to pull them out in front of the derivative symbol. So we're going to end up preferring this form to this form. In fact, this third log rule, changing exponents into coefficients, is going to produce much nicer forms for our derivatives. Similarly, these other log rules also produce nicer forms for derivatives because generally we don't like multiplication and division, right? You don't want to use the product rule or the quotient rule if you don't have to, but we love sums and differences because the derivative of a sum is just the sum of the derivatives. It's really easy to take the derivative of something plus something or something minus something. We don't need a special rule like the product rule or the quotient rule. If you can use log rules in this direction, changing forms that look like the left-hand side of the equal sign into forms that look like the right-hand side of the equal sign, you'll be making your derivatives, generally speaking, a lot easier. We've done that once, but we're not done, because what we now have with this 1/2 out of the way is the log of something times something, x squared and e to the x. That fits this first log rule. We can rewrite this as the natural log of x squared plus the natural log of e to the x. But be really careful. We turned one term, x squared e to the x, into two terms by putting this plus sign in here. The 1/2 is supposed to get multiplied by the entire thing, but the way it's written right now, the 1/2 only gets multiplied by the natural log of x squared. So as is often the case, when you change one term into two terms, when you introduce plus or minus signs, you got to be really careful with your parentheses. I need parentheses there, and then another set to close my derivative. And maybe you're like, cool, I got it from here. These are easy derivatives to take. Well, yes, but we don't need to be done. We can go even further. We have two different logs now. If you focus on the first one, the natural log of x squared, it again fits this third log rule. We can take this 2 and bring it down in front of this natural log. So instead of the natural log of x squared, I have 2 times the natural log of x. Similarly, over here, e to the x power, using this third log rule, I can take the x down in front of this natural log, so I get x times the natural log of e. At this point, we're done with our log rules, but there is a little bit of simplification that we can do before we do our calculus. I could get rid of these parentheses if I felt like it by taking the 1/2 and distributing it through. And I might recognize that the natural log of e is just equal to 1, because the natural log of anything is asking you the question, what power must you raise e up to change it into that anything? So since the implied e to the first power is equal to this e, the natural log of e is just 1. What I'm saying is this second term is really just an x, and when I distribute the 1/2 through, I get the natural log of x plus 1/2 x. We haven't done any calculus at all. This has all just been a lot of algebra. But through this process of algebra, we've changed a derivative that was really hard to take into a derivative that'll be super easy to take. The derivative of something plus something, that's just the derivative of the first thing plus the derivative of the second thing. The derivative of the first thing, the derivative of natural log of x, is just 1 over x. That's one of my building blocks. What about the derivative of 1/2 x? That's just equal to 1/2 times 1, in other words, 1/2. What I'm saying is that g prime of x can be written as what you see in purple here, or it can be written much simpler as what you see in green here. And while these two things are equivalent, this form is 100 times better when you're being asked to take the second derivative. Because the derivative of purple would suck, but the derivative of green is no big deal. To figure out g double prime of x, all you got to do is take the derivative of what we have here. Maybe you'd write that as x to the negative 1 power plus 1/2 to make it more conducive to your derivative rules. The derivative of x to the negative 1 power using the power rule is negative 1x to the negative 2. The derivative of 1/2, since it's a constant, is just 0. What I get as my final answer is negative 1 over x squared. Kind of cool to see how much this can simplify if you use these log rules. The moral of this story is don't forget these log rules. Anytime you're taking the derivative of any log of some ugly looking expression, think, can I rewrite that expression using the log rules in this order, left to right, to make future me, calculus me, really happy, to make the derivative easy to take? That's the second of the 3 things I want to show you in this video. The third and final thing I want to show you in this video is when we first learned the product and the quotient rule. I kind of proved the product rule to you, and I didn't prove the quotient rule at all. I think I made some sort of comment about how the quotient rule is really just a consequence of the product rule and this other rule that we'll learn later on. That other rule that we'll learn later on is what's called the chain rule. And the product rule and the chain rule allow you to eliminate the quotient rule if you don't want to use the quotient rule. I don't think you should eliminate the quotient rule. I think that you should look at a given problem and think about which of the different tools you have fit that problem the best. But if you wanted to eliminate the quotient rule, you absolutely could. For example, this problem right here, it looks like a very natural quotient rule problem, right? Is something divided by something. But if you rewrote this as the derivative of the sine of x times, instead of divided by, x squared minus 5x plus 1 to the negative 1 power, now you don't need the quotient rule anymore. So first convince yourself that these two expressions are equal. Raising something to the negative 1 power means 1 over that something. And sine of x times 1 over all this stuff would reproduce this fraction. What we have inside these parentheses is equal to what we have inside these parentheses, but these parentheses do not need the quotient rule. I got something times something, I use the product rule. I take the derivative of the first thing, sine of x in this case, and I multiply that by the second thing, x squared minus 5x plus 1 to the negative 1 power. To that I need to add the derivative of the second thing, x squared minus 5x plus 1 to the negative 1 power, times the first thing, that's sine of x. I have two d over dx symbols, meaning I have two derivatives I need to take. First one's pretty easy. The derivative of sine is just cosine. So I get cosine of x times x squared minus 5x plus 1 to the negative 1 power. But then over here, things are a little bit more complicated. Maybe you'd recognize that you need to use the chain rule here. The outer layer is the stuff raised up to the negative 1 power. The inner layer is the x squared minus 5x plus 1. So I take the derivative using the chain rule and I multiply that by sine of x. So that I don't get confused about where all the pieces go, I'm going to write the sine of x first, and then I'm going to figure out this derivative. To figure out this derivative, I use the power rule first, taking the negative 1 down in front, leave the x squared minus 5x plus 1 completely alone. My new exponent is 1 less than it used to be. But then I'm not done. I have to multiply that by the derivative of that inner layer, x squared minus 5x plus 1. The good news about this line is there's only one derivative left to take, and that derivative is something that's well within your reach. The derivative of x squared minus 5x plus 1 using our various polynomial rules, I guess I need parentheses here and here, is just equal to 2x minus 5. I'm done with d over dx symbols. I'm done with this problem. Can simplify this problem if I want, and maybe this is an instance where if I start to simplify things, you'll be able to see why I'm simplifying it. So let me rewrite some stuff. My first term is the cosine of x times all this stuff to the negative 1 power. But instead of raising it to the negative 1 power, I can just make it 1 over all this stuff. What I'm saying is this first term can be rewritten as this fraction. My second term I'm adding, but I also have this negative 1 floating around. So instead of adding something that ends up being negative, I can just subtract. What am I subtracting? Well, up top, I would have a sine of x for this sine of x. And then I would have a 2x minus 5 for this 2x minus 5. And instead of multiplying all that by x squared minus 5x plus 1 to the negative 2 power, I could divide all of that by x squared minus 5x plus 1 to the positive 2 power. I have two different fractions. If I felt the need, I could get a common denominator. My common denominator would be x squared minus 5x plus 1 squared. In order to get that common denominator, I'd multiply the top and the bottom here by x squared minus 5x plus 1. What that would give me is the cosine of x times x squared minus 5x plus 1 minus the sine of x times 2x minus 5, all divided by my common denominator, which is now x squared minus 5x plus 1 squared. Why did I do all this simplification? Because maybe looking at this form, you can see the quotient rule going on, right? The quotient rule tells me take the derivative of the top, derivative of sine is cosine, times the bottom left completely alone, there's that x squared minus 5x plus 1. From that, I want to subtract the derivative of the bottom, that's this 2x minus 5, times the top left completely alone, that's that sine of x. Then I want to divide that entire mess by the bottom, x squared minus 5x plus 1 squared. It's not a coincidence that this simplified to give us the same answer. I mean, you can almost see the pieces of it because when you rewrite this as a product, you get this exponent of a negative 1. And when you use the power rule on that exponent, that's going to produce a negative 2, which is going to end up being the bottom part squared. The old exponent of negative 1 gets brought down in front here, which is what changes the plus, which comes from using the product rule, into the minus, which you need for the quotient rule. The purpose of this example was not to say that this problem was easier to do without the quotient rule. In fact, I think in this specific example, it's harder to do it without the quotient rule. Just to make the point that it can be done without the quotient rule, using the product rule and the chain rule, because the quotient rule is really a consequence of the product and chain rules. And to really hammer that point home, I want to prove that fact to you. Maybe this example was enough of a proof for you, but it's really not a concrete proof. For a concrete proof, what I have to do is think about these two arbitrary functions, f and g, and take their derivative without using the quotient rule, and then showing that what I get from my answer is exactly the quotient rule. That proves the quotient rule. How can I do that? I got to rewrite it so it doesn't involve division, so I don't need the quotient rule. I'll say it's f times g to the negative 1 power that I'm taking the derivative of. Because f divided by g, no matter what f and g are equal to, is the same as f times g to the negative 1 power. Now we take the derivative. Can we take the derivative? Sure, just use the product rule. The product rule tells me the derivative of this product is the derivative of the first thing, the derivative of the f, which I can write as f prime, times the second thing left completely alone, g to the negative 1 power, plus the derivative of the second thing. This is going to be a little bit hard. You're supposed to see the chain rule in here. The outer function is the stuff raised up to the -1 power. The inner function is this function g. So when I take the derivative of g to the -1, I bring the -1 down in front, I leave the g completely alone, and I subtract 1 from my exponent to get a -2. But then I'm not done. I have to multiply all of that by the derivative of the inner function, the derivative of g, which is g prime. It's easy to get lost in what we're doing, but remember the idea here was to use the product rule. Derivative of the first thing times the second thing, derivative of the second thing times the first thing, that produces this f. As long as this expression here is equal to the quotient rule, I will have succeeded in proving the quotient rule. Is it equal? Absolutely it is. Because look, multiplying by g to the -1 power is the same as dividing by g, because g to the -1 is 1 over g. So instead of f prime times g to the -1, I can write f prime over g. Instead of adding this negative thing, I can subtract. This thing that I'm subtracting is a product of three things: g to the -2 power, g prime, and f. Instead of the g to the -2 power, I can put g squared down in the denominator. That leaves me with just the g prime and the f up in the numerator. What I have here is a difference of two fractions. If I wanted to subtract those fractions, I'd need a common denominator. To get a common denominator, I'd multiply the top and the bottom by g. If I multiplied the top and the bottom of this fraction by g, I'd have f prime g divided by g squared minus g prime f divided by g squared. And as long as I have a common denominator, I might as well subtract the numerators, giving me f prime g minus g prime f divided by g squared. If this looks or sounds familiar, it should. It's exactly the quotient rule. What we just proved is that the derivative of the quotient of two functions is just equal to this big mess. The quotient rule is a consequence of the product rule and the chain rule. I think that fact's kind of cool. And if you're going beyond calculus, it would be good for you to find that fact kind of cool. But our class isn't really a proofs class, so if I lost you somewhere in here, it's really not the end of the world. I'm going to link another one of those 3 blue, 1 brown videos to prove, I guess, in big air quotes, or at least to justify the chain rule. I find it really interesting. Hopefully you do as well. But that's all I got for this section.